In the last video, we had talked about charge accumulation on a capacitor, and we had derived an equation for it. Basically what happens is that if we have just a simple capacitor, resistor, battery circuit in series, when we first make the connection, there's a current that flows through here. The magnitude of it is just the battery voltage divided by the resistance, E over R. But then with that current, there's a charge accumulation on these capacitor plates with this polarity, as we discussed in the previous video, so that the voltage across the capacitor opposes the battery voltage. So as more and more charges accumulate, this voltage accumulates. So the voltage across the capacitor keeps resisting the battery voltage. Therefore, the magnitude of the current keeps decreasing until this voltage, the capacitor voltage, equals the battery voltage, and then the current is just zero. And then for the charging current, it is just from the positive battery terminal around like this. So it's going in this direction. Now, in the last video, we had determined that the equation for charge accumulation on the capacitor is this. And now, for a simple capacitor, resistor, battery in series like that, we had this equation for the current for the circuit. That's the charge on the capacitor, which is this. So if we substitute this for this, eventually we'll get this as an expression for the circuit current. And again, this is commensurate with what we just stated. At time t equals 0, that's 0. The current is just the battery voltage divided by the resistance. Then with time, this fraction becomes less and less, so eventually the current falls off to 0, and that's what we're showing here in the graph. Now, with this equation for the capacitor charge, of course, the voltage across the capacitor, that's just Q divided by C. So divide this by C, and that's the voltage across the capacitor at any time. Now again, QF divided by C, of course in general, Q equals C times V, but when the capacitor is fully charged, then that voltage is the battery voltage. So the final charge Q equals C times E. So QF divided by C, that's just the battery voltage. So here, we can just replace this with the battery voltage, and here is our equation for the voltage across the capacitor. And at time t equals 0, this is e to the 0, which is 1. 1 minus 0, so the voltage is 0. Then as time goes on, this becomes smaller and smaller, as we talked about in the last video. So we're subtracting a smaller and smaller number from 1, so eventually the voltage across the capacitor just becomes equal to E, the battery voltage, and it looks something like this. Now, in this video we want to consider, here we have our circuit. Capacitor is fully charged. There is no more current flowing, so we disconnect. And again, remember when it was flowing, it was in this direction. Now we disconnect this switch and connect this one. So now this charged capacitor can discharge through this resistance hooked to it. And this time the current will be in this direction. So the discharge current is opposite to the charging current. And of course, we'll have a voltage drop here, like this. So if we sum the voltages across, go ahead and say in this direction, here we'd have minus IR. Then we go across. Here we go minus to plus, simply plus the voltage across the capacitor, and in general, that's just Q divided by C. Of course, those voltage drops, some of the voltages across the circuit have to be zero. So we have this pretty simple looking equation, or we can say that bringing this over to here, we have minus IR equals minus QC. So these cancel. And then, but what is I? So we have IR equals Q divided by C. Remember, I is the instantaneous rate of charge with respect to time. So again, using simple calculus, I is dq dt. So we have this, and you probably see where we're going with this now. In general, the integral of dx over x is the natural log of x. So here we have dq and q, so we're going to bring this over to here. So we have dq over q equal, and we can take this over to here. We have 1 over RC, bring this over to here, and we have this simple equation. So it looks like we should be able to handle this pretty easily. We can integrate. Oh, one thing we should notice is that here we have dq dt equals q over c. Well, now, with time, the amount of capacitor charge is going to be decreasing as this goes across the circuit like this. So that means then that dq dt is going to be getting smaller over time. So dq dt is really a negative quantity. And again, the reason is the charge decreases over time, so its rate of decrease is not going to be a positive number. It's going to be a negative number. So let's put the minus sign over here. So we have it like this. Let's just write it a little bit neater. We have dq divided by q equals minus 1 over RC dt. And of course, that's a constant. The capacitance is a constant. So we can integrate like this, keep that to the outside, integrate here like this. We won't put limits in our integrals, but what do we have? The natural log of q equals minus, well, hold on, we're going to have this, but there's no limit, so we're also going to have arbitrary constant of integration. And let's see, this will equal, that's just going to be t, so you have minus t divided by RC plus this 2. We'll have an arbitrary constant of integration, and we can take this over to here. So we have it like this. But a constant minus a constant, that's just a constant. So we can call this K triple prime. So we place this with this. So we have that the natural log of Q equals this. And again, remember the way natural logarithms work. E to the natural log of x, that is just x. So we're going to raise this side of the equation, having it e to this power, and same thing here, having e to this power. But e to the ln of q, that's just going to be q. So the left side is just q equals e raised to this power. E to the minus t over rc plus this. And remember now how it works for exponentials. E, say, to the c plus d equals e to the c, e to the d. So we can write this as e to the minus t divided by rc times e to the k prime, e to this constant. Okay, but of course this is just a constant. It was just lumping two arbitrary integration constants together. This is a constant, so we have this raised to a constant power, so that's just going to be another constant number. We'll call it k. So we'll take this out and write k in its place. So we have this equation, q equals this. Q equals k times e to the minus t divided by rc. And q, of course, is the amount of charge in the capacitor, and as this discharges, q is going to be smaller and smaller. Now, let's go back to here. Remember what it was like at t equals 0 before we got it connected here at fully charged. We disconnect this. Then at time t equals 0, we connect it like this. At that moment in time when we do that, the charge on the capacitor was QF, its full capacitor charge. So here we can say when t equals 0, Q equals QF. So here then we can say that Q at time t equals 0, that is QF, that equals this K times E. T is 0, E to the 0. E to the 0 is 1. Any number raised to 0 is just 1. So we have that this constant K, that is the full charge in the capacitor, QF. So we'll put that right here. And again, as we explained in the last video, this is to a negative exponent, so as we go on, as time gets larger, this number becomes exponentially smaller. So all we're saying is that the charge on the capacitor initially was QF, was fully charged, and then when we throw this switch, it's just going to decrease exponentially. Now, that's the charge on the capacitor. What about the current? Well, current is just dq dt, so we can say I equals dq dt. So this is the amount of current on the capacitor. That's decreasing. Why? Because there's a current that flows through the circuit from the capacitor. And the rate of change of that charge, that's the current. So the current that's going to be going, this discharge current that's going to be going through our simple circuit, that will equal then the derivative of this side of the equation with respect to t. And that's just going to equal, with this constant QF, then the derivative of e to the minus t over RC, that will be minus 1 over RC, just times e to the minus t over RC. So we have that I, the discharge current, equals minus sign here, QF over RC times e to the minus t divided by RC. Now, what is QF divided by C? It's going to be the battery voltage. So we have our discharge current I equals minus QF over C, that's E. So you have E over R, E to the minus T divided by RC. So this is the equation for the current when we take our fully charged capacitor and put the switch over to here, so this switch is now open so that this capacitor can now discharge. And remember, this should make sense because at that instant, what is the voltage drop across the capacitor? It's E, because that capacitor is fully charged. So just at that instant, when we put the switch over to here, so this is a complete circuit now, at that instant in time, this voltage drop across there is equal to E. So instantaneously, what's going to be the amount of current? E divided by R. But of course, what's going to happen is more and more charges leave the capacitor, the voltage decreases, and the current eventually falls off to 0, which is what our equation right here tells us. But let's make some room, and let's write this at the top of the board and talk about in just a little bit more detail, and maybe we can sort of graph it out too. So we have our discharge current I equals minus E over R, E to the minus T divided by RC. And the minus sign indicates to us that the discharge current flows in an opposite direction to the charging current. Remember, we said earlier that when this was hooked up to the battery, the charging current was in this direction. The discharge current is in the opposite direction. So that's what that minus sign shows us. And again, as soon as we throw this switch so that this circuit is complete, at that moment in time, that voltage there is E. And that current is going to be E over R. Then, as these charges dissipate, this voltage keeps decreasing. And in fact, we had shown that over... Yeah, let's just show it right now then. Let's do it like this. we showed in the previous video that we had this equation for the charge in the capacitor, and we could substitute this for here, so we have this equation for the charging current, and that looks like this. So what it means is that going back, when we originally had it like this, take these away, and this was hooked up to the battery, this is current, this is time. So while this was charging now, when we had the charging current going, as we showed, initially the charging current has that value E over R, then it falls off. So the charging current looks like this. Now for the discharge, that's our charging current. Now the discharging current, and this is E over R. The charging current, as we discussed a few moments ago, starts off with the value of E over R and goes to 0. Well, now the discharge current, so now it's like this, there's no current. Now we go to here, catch it like this, and now there's going to be a discharge current, initially a value E over R. So it's down here, minus E over R. It's going in the opposite direction. So the discharge current starts like this, and then it too goes to 0. So it's going to look something like this. So this is the current while the capacitor is charging. This is the current when the capacitor is discharging. And again, we just derived this equation right here. That's for the discharge current. And then in the previous video, we derived this. This was our circuit current. Substitute this for this, and we have this is the equation for the charging current. The only difference is between these two is that this one, the discharge one, is a minus sign because it's going in the opposite direction. Okay, that's all we wanted to show for this video. In the next video, what we will do is we will start to consider more circuits where we have various capacitors combined either in series or parallel with various arrangements of resistors, and we'll solve more specific circuit type problems. And I think this video is number 62 now in our series. Anyway, the playlist is at the website digital-university.org.